Write the topic finding refracting angle or the prism angle. We call that prism angle. Write the topic. Okay. So here you have the prism table. This is the prism table. You get the prism, and at the center you just place the prism like this. You don't have to follow the previous. Remember, when you are leveling the prism, you had to follow some steps, right, to level the prism table. Here you don't have to, right? You already have leveled the prism table, so you don't have to level it again, right? So you just place the prism like this. Only requirement is, so you have the collimator here. So from the collimator, you have parallel light coming from the collimator. Only requirement is this parallel light has to be incident on the prism symmetrically, right? So what happens is, when the light is incident here, it reflects off like this. There's light refracting into the prism, but we don't consider the refracting, right? Here we take reflection of rays. So to identify this ray, you have the telescope. You can rotate it around this to identify these light rays or the images formed. Okay. So you bring the telescope here. Okay. So this is, let's say this is T1 position of the telescope. Let's say you see the slit, you know that slit, image of the slit like this. Now it is symmetrical, right? Because we have already leveled the prism table, it is symmetrical now, right? Everything is clear now. But the slit is slightly somewhere here, right? So when you get the image of the slit, you have to keep finding for the image of the slit, right? By rotating. Let's say you get a position like this. When you get a position like this, you lock the telescope. There's a screw, right? Then there's a knob at the side. You find, once you lock it, then you can fine adjust using that knob. And you can move the telescope slightly to this side. And what happens? You know the rays here, you can further rotate it slightly to this side, right? Then the image of the slit moves to this position, like this. So once it is moved to this position, now you take the reading. Now you have the right vernier scale and left vernier scale. From both you take the reading. You measure that angle, right? Let's say you got that angle as θ1. Okay, that is done. Now you have the value of that angle. Not an angle, just the reading here, right? Then what do? Then you move the telescope to this position till you find the image of the slit. Again, you might see the slit like this. It could be here or it could be here. Then you fine adjust till you get the image right on the crosswires, right? So this is the T2 position of the telescope, and let's say you measure the angle as θ2. Actually it is not an angle, it is just a reading, right? From the left and right, from the left vernier and right vernier, you take the measurement and take the average. That becomes the theta 2 value. Theta 2 value. Right. Then what do? From the difference of these two angles, you can measure this angle. So in theory, you know that this angle is twice as the prism angle, right? This angle is twice as the prism angle. So now what can we say? Theta 1 minus theta 2. If this is larger than 360, you can see it is not larger than 360, right? In the experiment. If you get an angle larger than 360, you just have to subtract that angle from 360. Let's say we didn't get a larger angle, like a reflecting angle. You didn't get a reflecting angle. You just get a angle that is less than 180. Large angle minus small angle. You need to get a positive value, right? So this is equal to twice the prism angle. So how do we find the prism angle? So A is equal to theta 1 divided by theta 1 minus theta 2 divided by 2. Right? So this is how you measure the prism angle. Okay. This is how we measure the prism angle, and take this down and thumbs up. Right. Here we use rays that is partially reflected, right? There are refracting rays. You know that the colors are divided, right from red to violet. Colors are divided, dispersed. We call that dispersion. Colors gets divided when it is refracting. When reflecting, colors does not get refracted. I mean dispersed, right? Here for this experiment we use reflection actually. We call this, there's a 20% partial reflection, right? We use a reflection. So for the light source, we can use either monochromatic light or a white light. It doesn't matter, right? Monochromatic means single color, meaning it is either red, blue, yellow, something like that. Monochromatic. In the experiment, if refraction is involved, you have to go for a monochromatic light. But here reflection is involved. So you can use either white color light or monochromatic light. It doesn't matter, right? Below this, write down. Below this, write down. Here, monochromatic light beam, monochromatic light source, monochromatic light source is not essential. Monochromatic light source is not essential since only partial reflection is used. Since partial reflection is used. Then the next point, to increase the accuracy of angles, consider average value, gained from R and L verniers, right and left, right? Gain from R and left verniers. Gain from R and L verniers. Then the third point. Note that, third point, note that slit should be very thin. Slit should be very thin to get more precise readings. Slit should be very thin to get more precise readings. Right? So the last point I'll explain that. Let's say you get the slit like this, right? What happens now? You cannot know whether this is precise here, right? You might read the angle here or here or here. So you have to minimize that as much as possible. There's a limit you can make it thin, right? Because otherwise, no, you have to get sufficient amount of light through the slit. Otherwise, you won't see an image. But you have to make it as thin as possible, right? So the measurement, reading would be more precise, right? Because the variation is small now, right? So that is what the third point means. Okay. Then we'll consider how to get, how to measure angle of deviation, right? Angle of deviation. Write down the topic, measuring angle of deviation. That is simple D, not minimum deviation, just the angle of deviation, simple D. Okay? Right. So when the deviation happens, there is a refraction, right? So whenever there's a refraction, there's always a dispersion of light. The light gets separated into colors. So those color spectrum disturbs the experiment, right? So for this part, you have to use a monochromatic light. It is either red, blue, anything like that. Usually we use a sodium bulb, right? Which is yellow in color. So for the light source, here we use monochromatic, right? Then you have the collimator. Then here you have the prism table. Okay. So this is collimator. So here you have the telescope, right? Telescope. So align with this light ray, you have to fix the telescope here. Okay. We haven't put the prism, you have removed the prism, right? You need to get this reading. So the light rays goes like this directly. So how do you know whether you don't see these light rays, right? All you see is in the view field, you see this slit actually. Then you lock it here, the telescope, you lock the telescope. Then you fine adjust till you get the slit onto the crosswire. Right? You fine adjust till you get the slit, image of the slit onto the crosswire. Then we can say all the light rays from here has entered the telescope and they are aligned, right? Then what do? You take the reading. You take the reading of the related angle, right? Let's say that is theta 1. Okay. Right? So that is the first step. This is the T1 position of the telescope. Then what do? We place, because we need to find the angle of deviation, right? Then we place the prism. Anywhere you like, you can place the prism here, like this, right? Prism like this, you can place it. Then what happens? So the light rays coming from the collimator is incident on this surface. And this is the angle of incidence, right? Angle of incidence is here. It is supposed to go to this direction, but due to the prism, it gets refracted. Let's say like this. Then again it refracts to here. So this is the emergent ray. So the angle between this ray and this ray is the angle of deviation, right? So to figure this ray, you have to move the telescope, rotate the telescope from here to here. Let's say here, like this. So this is the T2 position. Again, you fine adjust that till you get the image on the crosswires and get the reading. That is theta 2. Then what do? So D is equal to what? Theta 2 minus theta 1. Right? From the you always have to get the positive value, right? So you can see it is not possible for this to get like a reflective angle, right? This is an acute angle. So if you get a reflective angle, you have to subtract this value from 360 and get the angle of deviation, right? Angle of deviation, simple D. Okay. Take it down and thumbs up once you have taken it down. You can take this down as I'm explaining, right? Doesn't matter. But you have to pay attention as well. Right. So this is how you measure angle of deviation for any incident angle. For any incident angle, this is how we measure that, right? Okay. Then write the topic measuring angle of minimum deviation. Measuring angle of minimum deviation within brackets capital D. Measuring angle of minimum deviation capital D and simple n. Simple n means refractive index, right? Right? Measuring angle of minimum deviation and refractive index simple n. Right? So similarly we can find the angle of minimum deviation. But you have to recognize, only difference is you have to recognize where that minimum deviation happens. Okay? Right. So if you remember this graph from the theory, so from a small value, you keep increasing incident angle. So when you keep increasing the incident angle, what happens to the angle of deviation? This is not minimum deviation, right? This is deviation. Deviation rapidly decreases. And after minimum value, it starts to increase. So this is what we call angle of minimum deviation. So you know at that angle, I and R, those are say equal, right? Right. Not R, I mean I1 and I2, those are equal. But here you have to find minimum angle. You have to recognize when this happens, right? Similarly, you can do this. So how do we do this? You can rotate the prism angle, prism table, right? You can independently rotate the prism table. So there's a screw, you have to loosen that screw and you can start rotating this prism angle without slipping the prism, right? You have to slowly rotate that. If you quickly rotate that, this would slip. You have to slowly rotate this, right? Okay, let's see what happens. So I have to start from a small incident angle, right? See that? Small incident angle, right? So I have to, let's say you have to rotate this somewhere here in order to make this small. This I should be small, right? When you rotate it here, I gets small, right? Then you start rotate to this side. Once you take I to a small angle, you can start rotating prism table to this side, right? Now what happens? When you are rotating the prism table to this side, do you understand that with the prism table, this prism also rotates. This I increases, right? When you rotate the prism table here, this I increases like this. I increases. So when I increases, what happens to simple D? It decreases. See that? When I increases, simple D decreases. So I increases, simple D decreases. So you can see this ray is moving to this side. When you are rotating the prism angle, prism table, let's say this is like a mouth. This mouth is closing, starts closing. So you have to follow this slit. Slit starts to move to out of this view field, right? Out of the view field. So you have to follow. So this ray is getting like this. You have to follow that using the telescope, right? So let's say this is the cross wires. Initially the slit was here. Then let's say slit moved to this position, right? This position. As you are rotating the prism table, the slit moved from here to here. Image of the slit. Let's say after this position, right after this position, slit starts to move to the opposite direction. You have to identify this position, right? Right after this position, the slit, image of the slit, starts to move to opposite direction. Why is that? After this point, further increase of I causes D to increase now. Now understand, initially this ray is moving to this side, right? Move to this side. But when you further keep rotating the prism table, D starts to increase. Then initially the ray was moving to this side. Now it starts to move to other side, opposite side. Then that is what you see. The slit starts to move to opposite side. You know that starting position happens at the D minimum value, right? Then you have to identify this location and you stop the telescope. Then you fine adjust till you get the image of the slit onto the cross wires, right? So it's here, it starts to move to here, then you get it to the cross wires. Then take that reading. Let's say theta. So that is theta. Then D should be what? Theta minus T1. You just take the difference, right? Large angle minus small angle. So D is theta minus theta 1. So that is the angle of minimum deviation. So that is the only thing that happens, right? This slit starts to move to opposite side. The starting position is related to this minimum angle. Understood? Right. That is all you have to do. So at that point, you have to stop moving the prism table, right? Then you have to follow using the telescope. Right. Draw this one and draw this one as well, right? This one as well. Then write this equation. Right. You can refer this again, right? The more you refer, the more clearer this will get, right? Okay. So now we have measured the prism angle and angle of minimum deviation. Prism angle and angle of minimum deviation, right? Then you can find the prism material. So you have this equation divided by sin A over 2. So A is known, D is known. You just have to substitute these values and simply you can find the refractive index of the prism material. That's all you have to do, right? You can simply find the refractive index of the prism angle. Sorry, prism material. Write that equation down. Here, you must use monochromatic light, right? Monochromatic light you must use because there's refraction. Sorry, there's dispersion because due to the refraction, right? So for this experiment, you have to use monochromatic light. Okay, monochromatic light. Take that equation down and you can find that using that equation, you can easily find the refractive index. Okay, so spectrometer practicals, this is one of the most important, right? And many students have misunderstood this experiment. They frequently ask questions from that. I'll send the past paper years that they have asked questions onto the group. Then you can do those questions and practice. So once we finish that, refer the experiment again, the note I have given again, and you can refer the PDF as well, right? So that is a detailed PDF. And do the questions. Do the past paper questions and that's all, right? Then you can have a in-depth understanding of spectrometer and you don't have to worry about spectrometer again, right? Right. I'll send the past paper questions and we'll wind up the spectrometer part here. And tomorrow there will be a class at 8 p.m. around 8 to 8:30 to discuss how to find the focal length of a convex lens and a concave lens, right? So once we did that, all the practicals in light optic parts are covered, right? Okay. So we'll see you tomorrow at 8 p.m.